Thank you very much. Sorry for being a bit, for the organizers, for being disorganized myself this morning and arriving late. It's just confusion with my calendar. Anyway, I'm glad to be here, and I want to welcome the 80% of you or so that are new to Stanford, and it's great to see these new faces every year, and I hope you have a wonderful year. And I'm happy here to be able to talk to you about the work we're doing, and I'm going to try and connect a couple of dots here today related to water and energy, and let's see how this all works. So first of all, I've got a picture here that shows global water demand, and these are showing from 2005 expected increase to 2030, from 4,200 cubic kilometers per year to 6,800 cubic kilometers per year. That's the projection that's been made, and you can see what fractions go for agricultural use, industrial use, and residential. 6,800 cubic kilometers per year. That's a number to keep in mind now. So if we look at how much fresh water does nature produce, it produces, amazingly, through the sun, through the treatment system, solar treatment system that we have, 107,000 cubic kilometers per year. We only need about 7,000 of those. So you could ask, what's the problem here, right? There's huge amounts of fresh water being created through the sun. So the problem is that in many urban centers, they're located where there's little fresh water. It's a question of where the demand is. Okay, so if you look at the population density here for the state of California, you can see it's dense in regions where there's almost no water. Okay, and in the near future, this challenge is going to become even greater for the United States. So you're looking at projected trends in population and increases and decreases that will occur in different parts of the country, but in particular, in the water scarce regions, populations are going to go up. That's the projection. So it becomes even a more serious issue, this question of water demand and how we'll satisfy this water demand. But this isn't just a problem for the United States. Here's another country that has the same problem. Some of you familiar with this country, right? A fair number, I'm guessing, okay? Look at the population density here. Okay, what do we see? And where it's high density, we see a lot of high density up in the north, and we have a lot of rain down in the south. So it's exactly the opposite of California, right? So in one case, we're going from north to south with our movement of water. That's how we've solved this problem, right? We transport large amounts of water using large amounts of energy. And in California, from north to south, we're moving about 13 billion cubic meters per year. And in China, the plan is to move 45 billion cubic meters per year from south to north. So it's a huge transportation issue there and involving a lot of water and a lot of energy. So in terms of the energy demand, for us to do this in California, we need about 2 kilowatt hours or more to move, depending on where you're dropping the water off, 2 kilowatt hours per cubic meter of water moved from north to south. Some number bigger than that. Now keep that number in your head, 2, and then we're going to look at what are the options, other options that could compete with moving water over vast distances in space. So the question is, can we do better, right? And so we want to think about, well, are there local water supplies that we could tap? And of course, one that always people bring up and comes to mind is seawater. We could get the water from a local supply, which would be along the coast. If you're located along the coast, you could use the seawater as a local source, remove the salt, and then you're in business, right? That would be one approach. Another is from wastewater. It turns out that wastewater, believe it or not, is where people are. It's local, right? It's always there. Okay, so we've got that as another option for a local source of water that could be tapped. So if we look at seawater and we compare it to wastewater, let's just do a side-by-side comparison in terms of what's in seawater and what's in wastewater. In both, we have salt, we have organic matter, and we have nutrients. If we look at the seawater, it has about 35,000 milligrams per liter, about 3.5% of salt. 3.5%. Domestic wastewater has about 500 milligrams per liter. A teeny fraction of seawater, right? In terms of the salt contamination we want to look at it that way. Wastewater, by contrast, has this organic carbon, which is both in a dissolved and a suspended form, about 50-50, a little close to that. And you can see the amount that's there. And also there's nutrients in wastewater, which are lacking in seawater. Okay, so there's the big difference between these two. Lots of salt in seawater, very little nutrients, comparatively low nutrients, and comparatively low in terms of organic carbon. So let's focus on the salt. And let's ask some questions about the salt. If we look at the energy for desalination and removing that salt from seawater, how much would it take to remove that salt from seawater? Well, it turns out that if these are in kilowatt hours per cubic meter, current value for removing salt from seawater using reverse osmosis technology is greater than 3. Greater than 3 kilowatt hours per cubic meter. Now, what was the number I gave you for transporting water from Northern California to Southern California? So here we've got a process that is significantly more energy intensive than moving that water all the way from north to south. Okay? Now, on the other hand, if we want to remove the salt from treated wastewater, it's hardly anything by comparison, right? It's less than 0.6. And I've also listed there thermodynamic limits. You can calculate for the concentrations of salt that are in seawater and for the concentrations of salt that are in treated wastewater, you can calculate how low it could go in theory. And you can see for seawater, we're never going to do better than 0.8. Okay, it's just a limit, a thermodynamic limit. We can't beat that. And on the other hand, with treated wastewater, you could go down to 0.03. So we see a huge energy advantage here when we're talking about purification of treated wastewater and removal of salt compared to seawater. Huge advantage. So now let's focus a little bit more on the other two parts that are in this comparison, the organic matter and the organic carbon and the nutrients. And you notice in this case, we'd say, oh, advantage seawater, right? Advantage seawater. But is it really? Okay, it turns out wastewater treatment requires about 3% of the electric load of developed countries. And conventional treatment, when we treat using conventional wastewater treatment technology, when we treat wastewater, it requires about 0.6 kilowatt hours per cubic meter to do that using conventional technology. That's used to get rid of the organic matter and the nitrogen that's in the wastewater that we just saw. That's essentially what it does. Okay, so typically about half of that energy requirement, about 0.3 kilowatt hours per cubic meter, is needed just to supply air to the microorganisms that are used to degrade the organic matter and remove the nitrogen. Okay, it's just oxygen. Okay. So here's a plant, treatment plant close to us that we've worked with the people there for many years now at Palo Alto to understand energy use at that plant. And they did this audit, and we've worked with them understanding the audit. And you can see here the kilowatt hours per cubic meter for each of the different units as you move through a wastewater treatment train, where you remove different parts of the different aspects of the wastewater are treated, or I should say components of the wastewater are removed as you move through the train. And what you notice in this case at Palo Alto treatment plant, they do aerobic treatment, and there's no anaerobic treatment for production of methane, okay? Aerobic treatment to remove the organic matter that's present. They also remove the nitrogen that's present as ammonia by burning it essentially to nitrate. And then the last thing is they have this incinerator that they use to get rid of the solids, and it's extremely energy intensive. They have to import energy for this. And so altogether, they end up using 0.9 kilowatt hours per cubic meter. That's Palo Alto. It was built in the 70s in that time frame, and most of the wastewater treatment plants in the Bay Area and in the United States were built about that time. They've all basically reached their design life. Okay. So a typical plant, as I said before, uses 0.6 kilowatt hours per cubic meter. The reason this plant is high is because of the incinerator. That's the real reason. Otherwise, it would be below average. So if we look at what else could be done, rather than taking these organics and essentially burning them through providing lots of air or incinerating them, what other thing could we do? If we look at the energy that's basically embodied, chemical energy embodied in this wastewater organic matter, what we see is that if we were to take the organic matter out of the wastewater and burn it, it could generate, in theory, 1.7 kilowatt hours per cubic meter. It could generate it. rather than being a net energy sink. It could be producing energy. And the same with the nitrogen, the reduced forms of nitrogen. Rather than requiring energy, they could be used to produce energy, and we'll show you how here in a little bit with research we're doing. So it turns out, remember that number, 2 kilowatt hours per cubic meter to move the wastewater or the water from north to south? That's about how much energy there is in chemical energy in wastewater embodied there that could be harvested. So it turns out wastewater has 3 to 4 times more energy than is needed to treat it. 3 to 4 times. So you can easily envision energy neutral wastewater treatment. So conventional treatment with anaerobic digestion of solids is accomplished this way. You essentially have wastewater coming in. Remember, I told you that some of the organic matter is dissolved and some of it is present in a suspended form that can be settled out. So those suspended matter is typically moved to an anaerobic digester like I've showing here. And you can see that you can produce energy from that. Now, this would be a conventional process used, for example, today at the city of San Jose or Sunnyvale or East Bay Mud. So there's many places around the bay that they do this. But the other part, the dissolved organics, are typically treated aerobically. Microbial communities that self-assemble are used to burn, essentially, these organics, and the biosolids produced are transferred to the digester to produce some energy. A lot of energy, though, is required for this aeration step. So we've looked at the energy balance at the city of Palo Alto, and we obtained a baseline for essentially looking at the organic matter flowing into the plant and the energy that's being lost in the treatment process, which involves right now aeration and incineration, as I described. And you can see how much energy is being lost. If they were just to implement a conventional anaerobic digestion process with the organic matter, like I just showed you, they could decrease significantly from 129,000 kilowatt hours per day imported. They could decrease that down to 41,000 kilowatt hours per day. And this is work that's being done by a grad student working with me, Unjung Lee. And this is sort of a systems level approach that we're trying to take to that problem. So it turns out that that other part of the organic matter that we're not yet recovering methane from could be used to recover methane. So the dissolved organics part, that stream, we could put it in an anaerobic reactor and produce more biogas. And there's other technologies out there that could also generate energy. And we're working on some. But here's one example of a promising process. Professor McCarty, who's a emeritus professor at Stanford and also working at Inha University in Korea, they developed a process where you can take this dissolved fraction and put it through a unit that looks like this. I hope you see that. Yep. And then it goes to membrane filtration. They purge it with air. And essentially this gives very efficient, it turns out, efficient treatment of the dissolved organic fraction. Okay, in some places, now we still have this issue of the nitrogen removal. And in some places, nitrogen can be used for fertilizer. Here's an example of that at Monterey. And other places, we have to remove the nitrogen and get it out. And it's being done in this area at all these different treatment plants, many different treatment plants around the bay. It turns out that the conventional process used to remove nitrogen is energy intensive, and it can incidentally release nitrous oxide that contributes to global warming and damages the ozone layer. So if we look at conventional nitrogen removal, and here's some little bit of chemistry, and the process that's used to do this, we start with a mole of ammonia, and you can add up the oxygen that's used and the electrons that are used to do this process to get it to nitrogen gas and remove the nitrogen from the water so that it's not fertilizing the Bay Area, for example. And it turns out that removal of a mole of nitrogen requires about 2 moles of oxygen and 9 moles of electrons and generates biosolids that store about 4 moles of electrons. It turns out that these 9 moles of electrons could have been used to make a little more than a mole of methane. So we're losing the opportunity to generate energy when we do this process, this conventional process. Now, a new process we're looking at takes advantage of the fact that this process goes through nitrous oxide. And we say, well, what if we just stop this process right at nitrous oxide? Okay? So it turns out nitrous oxide is like methane. It's both a potent greenhouse gas and it can be used as a fuel. Okay, and I learned this from Yaniv Shearson, who showed up at my door one day, he's working with Brian Cantwell in aeronautics and astronautics. They're generating, using nitrous oxide as a fuel. They can run these little cool looking devices, as you see here, little engines essentially, okay? And so the idea that we're taking now and working on is we take ammonia to nitrite, convert it to nitrous oxide, and then we decompose that, and that can be decomposed as shown here. And this is done in race cars, as you may know. And if there's time in the question and answer, I'll show you something on that. And then two methods. Biological PHB is a method we use to convert nitrite to nitrous oxide, or a chemical process. And it turns out if you do this, then nitrous oxide is a better oxidant than oxygen, so we get more energy from these engines. And that's the big advantage here. It gives a boost, an energy boost. Okay. So we're treating real wastewater right now from digesters, anaerobic digesters from Sunnyvale, California. We've also been doing East Bay mud more recently and getting high efficiency of conversion of nitrate to the nitrous. So the summary is that if we look at this process, you can do the stoichiometry here, and if we remove 1 mole of nitrogen, we need 1.3 moles of oxygen, 4 moles of electrons. So we have significantly reduced the oxygen requirement. We've decreased the amount of biosolids produced, and we've increased the amount of methane that can be produced, or methane equivalents that can be produced. Okay? So this isn't yet scaled up. We're working with groups around the Bay Area to do that. It uses a rapid process. We could maybe get phosphorus removal as well with this process, and we think it will be flexible for retrofits of the existing systems. If we look at then seawater and wastewater again, there's the energy demands, and we say, let's get the salt out of seawater. This is what it takes, about 3 kilowatt hours per cubic meter. Using conventional treated wastewater and desalination, it would take this much energy now to get the water, higher quality water. In the future, we could potentially get even lower than that. And so I'm showing the options where you have salt removal, but we can surely get to the point where we can get the organic and nitrogen out without any net energy expenditure. So distributed treatment is another thing that we were interested in. This is where you take the carbon out of the sewage out of a sewer and remove the carbon, disinfect it, and then use it for local uses. Okay. Another option is to remove even more contaminants like the nitrogen and phosphorus, and then it can be used for higher level things. And if you remove the salt out, you can get very high level uses. And as I showed before, we can estimate now what we could be in terms of energy with doing all of those 3 steps and tailoring the water then for different applications locally. So you can imagine hybrid water energy systems that might look, water is recovered in different local places, reused locally through local treatment systems, okay, like that. And we might even have some places where it makes sense to recover energy as well from these organics. And in the future, what I expect is that we'll have more and more integrated water and organics management. So here's wastewater going through its treatment process to get clean water. From that, we get the solids out, and you could have organic waste that is collected in another way that is combined with these organics here, and we digest them, recover nitrogen and phosphorus, and we create a whole variety of products. So wastewater treatment plants become resource recovery centers. And this is just showing us a place I was just to 2 weeks ago, Sejong, South Korea. It's a city in the center of South Korea they're building. And I just want to show you that here's a place where they're doing integrated organics waste management. So biosolids are being produced from the wastewater and digested here. But they also take food waste and plastic, and they separate them through this interesting vacuum collection system. You put this stuff in what looks like a mailbox here, and it just sucks it. And then it separates the plastic from the food. And the food is digested in these digesters, and the plastic is converted into pellets that they incinerate. And then here's, this is East Bay mud here. And this is, I think, the first wastewater treatment plant in the United States. It's energy positive, producing wastewater energy from biosolids. And they've done it by bringing in organics from all around the community from different sources, food waste, fats, oils, and grease, and so on. And they're digesting them in their digesters and producing more energy now than they bring in. So it's a net energy exporter. And so that's the end of my presentation. I do want to advertise a couple of classes that I teach. 177, Aquatic Chemistry and Biology. If you have that class, you can take the subsequent class, Environmental Biotechnology, which has to do with these kinds of use of microorganisms to recover clean water, clean energy, and also valuable materials. Thanks. So we can take questions. I also have if you're interested, I have a little teeny video clip I can show that would tie into Professor Biker's presentation just a few minutes ago. But it's up to you. You want to see the video? Okay. So I'm going to ask you which of these cars here, and this is something for Professor Biker to consider in the future, if he's still here. But there's no audio, so don't need to worry. We couldn't get the audio part. But this, I want you to guess which of these really hot cars here is going to have nitrous oxide. Okay. Okay, you see all these hot cars? Corvette, yeah. Ferrari, Porsche. They're off. Okay. Which car? Which car? Which one has the nitrous? Can you guess? Yep, we have a winner right there. Okay. Okay, you'll beat up Jag. So that's the one that wins the race here. Okay. Just want to point that out. Nitrous oxide is commonly used technology then in the automobile industry, right? Race car industry. And some of you might have seen the movie Mad Max, where they used nitrous oxide in the climactic final scene to allow for the final battle scene. And nitrous oxide was used in that movie too. So, okay, just for your amusement. If you have questions, yes.
So with more and more people moving to areas with strained water resources, is there any discussion about land use patterns or population trying to keep, say, maybe we shouldn't be growing areas like Las Vegas and Phoenix?
Yeah, I think a lot of people are thinking about those issues. Our group focuses mainly on the technologies that are needed to improve the situation, right? And but I think what you're pointing out, those issues you're pointing out, are extremely important issues, and we need to be asking those questions, and the communities need to ask and be asking questions themselves. So, yeah, completely agree with you. Yes.
So climate change is going to affect salinity content in water. One of the solutions being discussed is using desalination techniques. And you were showing a lot of great reasons why there's treatment of other types of water, wastewater in particular. Have you read or have you seen much discussion about transborder water treatment solutions? For example, Colorado River between the United States and Mexico, that's going to be significantly affected in the next 50 or so years. How does wastewater treatment fit into that equation?
That's an interesting question. Well, to the degree that you increase the salinity of the source water that's used for a community, you're going to increase the energy invested to try and clean it up to the standards needed, certainly for drinking, right? Sometimes you can remove enough salinity to allow it to be used for other purposes, and irrigation applications and toilets and other things like that. Don't need to worry about it in toilets. In fact, in Hong Kong, they use salt water to flush toilets. So, so that's not, you have to think about the application of the water. That's one of the things we need to consider there. Yes?
So it seems to me that there may be two major hurdles in getting wastewater treatment accepted. One of them is the yuck factor, and the other one is that it seems that you have to have more infrastructure installed. You have to have two separate sets of piping in your house, one for potable water, one for non-potable water. And how do you think we're going to get past these hurdles, and how long is it?
Okay, two questions: yuck factor, and the other one was this question of really about, what was it again? Yuck infrastructure, yuck factor, infrastructure. Okay, so yuck factor. Well, if the demand is severe enough, people tend to overcome the yuck factor. Is what I've noticed. When it's really severe, when there's severe droughts, people finally get it. Okay. And the other thing is education is important there. And also we need to address some of the technical concerns. People are concerned, some are concerned about contaminants of emerging concern that could be persistent in wastewater. So depending on the applications of the wastewater, and it needs to have those things removed. And some are difficult to remove. So that's an issue that may need to be addressed for protection of public health in some applications. So I'm saying there's both technology and education and the other, right? Really, the demand side is going to be impacting that whole discussion. In terms of the infrastructure, yeah, it's a challenge to to consider how to rebuild the infrastructure if you have an existing infrastructure. If you don't have an existing infrastructure, you do it right the first time. Where you have an existing infrastructure, we have to think very cleverly, and we have, actually, that's something we are thinking deeply about. San Francisco Public Utilities Commission is heavily involved in that, as you can imagine. How can we take advantage of the existing infrastructure with minimal changes to it to get us a good outcome in terms of water reuse? So gray water, for example, is one example of a place where probably some minor changes can be made to do things at a local scale and a household scale with gray water that would be useful. But we have regulatory issues and other things that need to be addressed to do that. But this also can be addressed through cluster scale treatment, where you decrease the amount of pipe that's needed to deliver water to households and to places where the water is needed. Yeah. Mm-hmm. Yes.
So if you're drinking your gray water, you have less for downstream users, environmental flow, and groundwater recharge. Could you touch on, well, which is not necessarily a problem in the Bay Area, because it's just going to the ocean, but somewhere like the Great Basin?
Yeah, we actually have to look at everything in an integrated way, and you're right to ask that question. So when we do these, when we think about watersheds, we need to think holistically about the watershed and all the uses within the watershed. Otherwise, we aren't going to get good solutions that are politically acceptable or even fair, right? So those kinds of things have to be simulated, and that's one of the things we're trying to, we are working on. There are models being developed for the watershed, at the watershed level, in the case in this area, and on the Front Range of Colorado, for example, watershed level, and at the smaller catchment levels that fit into those watersheds. And we need to understand the whole big picture. You're exactly right. Mm-hmm. 1 minute. We have one more question. Yes.
So it sounds like a very attractive proposition. You can, collect water that was normally just thrown away as wastewater. You can be collecting it to be useful, and you can even have net energy gain from it. What's the difficulty in selling this to communities? Because I can imagine the costs must be considerable if it's not being widely adopted.
Actually, really, the issue here is all the wastewater treatment infrastructure has had its design life in the United States. It needs to be rechanged. Leadership is needed within the communities, informed leadership, to help the communities mobilize in the correct way. I always like to use the example of San Luis Obispo. I go down there, they're using reclaimed water, and my wife has a house there. I go down there, and they have a little park there. There's a little park, and the children are out playing. Everyone knows it's reclaimed water being used to irrigate there, and it's got notification there. It's beautiful, beautiful. And it's called, San Luis Obispo named the happiest city in America. Happiest city in America. Well, they're using reclaimed water. It's not killing anybody, not harming their happiness. Okay? And why? It's because, I think, because of incredibly smart city planning and an informed electorate. I think that's critical.